Any better? Okay, fantastic. Okay, yes, so good afternoon, everyone. Thanks very much for sticking around right to the end of the conference. And thank you very much to the organisers for asking me to come and speak at this wonderful NISQ conference. It will become clear as my talk progresses that it might have been better suited to a different conference, PrevLASK, which is the conference on precise and very large-scale quantum devices. You're very welcome to use that for next year's event if you like. But I hope that, nevertheless, what I'm going to say is of some interest to the audience here, because firstly, maybe the techniques and the approach might be of some use in the NISQ era as well, and also perhaps the results will highlight some of the challenges that we face in applying quantum algorithms in this kind of near-term context. Okay, so what I want to talk about is applications of quantum computers, and what I'm going to say, in fact, picks up on some themes from Krista and Elizabeth's talks about what we're going to do with these quantum computers once we have them. So there are many papers out there presenting quantum algorithms of various forms, solving various problems. If you go to the Quantum Algorithm Zoo website, you'll see literally hundreds of papers on there about quantum algorithms. But there aren't so many cases where quantum algorithm has been applied to some problem which I would say is practically relevant, whatever that means, and where the complexity of that quantum algorithm has been calculated in detail, taking into account all of the relevant overheads and costs. So some very nice cases where people have done this over the last few years are some problems to do with quantum simulation first. So there's this nitrogen fixation example, which we heard about earlier, problems to do with condensed matter physics, such as many-body localization, and also quantum chemistry. And these are cases where people have firstly thought about the quantum algorithm very hard and optimized this a lot, and then also worked out exactly how many gates the algorithm is going to use for solving some problem of interest, and also sometimes even worked out the overhead from any fault tolerance that we need to run the algorithm. And this has been done in some cases for quantum simulation, and it's also being done for integer factorization and some other problems in cryptography. And these are all very nice examples, and some of these cases are arguably, I guess, approaching the NISQ era in the sense that we might be able to run the algorithms with around 100 logical qubits and maybe 10 to the 8 quantum gates or something like this. So this is not NISQ, but it's better than, let's say, 10 to the 20 gates and 10,000 logical qubits. So this is very nice, and these are all cases where the theoretical quantum algorithm achieves an exponential speedup over our best classical algorithms. So these are cases which we think are very hard to solve classically, so places where we might hope to see nice quantum speedups. But there are some people out there who don't care about either simulation of quantum systems or cryptography. Right? And there are many problems in the world which don't fit into either of these categories. And it would be very nice to understand what quantum computers can do in a more general context. And that's what this talk's about today. What I'm interested in is trying to find some, what you might call, truly general interest application of quantum computers. So an application of quantum computers that many different people, many different organizations might want to run that solves many different problems that might be useful perhaps in our everyday lives. And there are a few different criteria that I'd like to satisfy for such an application of quantum computers. So firstly, I would like there to be a quantum algorithm for solving the problem that has provable correctness and also provable performance bounds. Right? So this already rules out a lot of the heuristic algorithms that we have in this NISQ era, but I think personally that at a stage where we don't have large enough quantum computers that we can run these algorithms on, it's nice to have some confidence that they are going to outperform our best classical algorithms. Of course, it's not a requirement, but it's a nice thing to have. Also, I would like the algorithm that runs on the quantum computer to solve a problem of interest in a reasonable time, like let's say at most 1 day. So there are many quantum algorithms that achieve asymptotic speedups over their classical counterparts, like maybe square root type speedups, maybe exponential type speedups. So if you have such an asymptotic speedup, then you can make the advantage of the quantum computer over the classical computer as large as you want just by making the problem size as large as you want. But on the other hand, if the problem size you need to get to in order to see a decent advantage for the quantum computer, if the problem size is so large that you might need to run the quantum computer for a year or 10 years to solve the problem, then that quantum algorithm is probably not one that people are really going to run in practice. Many people are not willing to wait for a year to solve their problem, but they might be willing to wait for, let's say, a day to solve the problem. And this is a particularly tricky constraint because some quantum algorithms that we want to run are somehow inherently sequential, such as Grover's algorithm and simulating time dynamics of quantum systems. Both of these have a sort of sequential aspect to them, which maybe makes it a bit harder to parallelize them. Okay. And also, maybe it's an obvious point, this quantum algorithm, it ought to outperform the best classical algorithm that we have running on real-world hardware that we have today, not a contrived algorithm that was the best one we had 20 years ago, or perhaps the best hardware that we had 50 years ago. This is something that Krista said as well. We should really be comparing against modern day, current techniques. So these are the three main sort of goals that I'm going to try and achieve during this talk today, and we'll see how far we get. And then there's an additional thing, which I guess you call a stretch goal, which is that it'd be really nice if our quantum algorithm would be suitable to be run on a NISQ machine and we could actually run it in the near future. But as we'll see, I definitely will not achieve that goal in this talk. Okay. So there are two applications that I want to focus on today, and they're very sort of fundamental mathematical computer scientific problems. They're graph k-coloring and boolean k-satisfiability, or k-sat. So probably everyone here is familiar with these, but just to refresh your memory. So in k-coloring, we've got a graph, a connection of vertices and edges, and we want to assign one of k colors to each vertex such that no two adjacent vertices have the same color. So this is a valid 3 coloring of this graph. And in k-sat, or boolean satisfiability, we have a boolean formula, which is a collection of and, or, and not gates in conjunctive normal form, as I've written here, where we've got some clauses which are variables, perhaps with nots in front of them. Then they're ored together, and then we have ands of the different clauses. And we want to find an assignment to the variables that satisfies all of the clauses, such that this whole thing evaluates to true or to 1. Okay, so these are both very fundamental problems in computer science. They're both NP-complete, and they each have a very huge number of direct applications, even without considering the fact they're NP-complete, so any other problem in NP can be reduced to them. So SAT, for example, we can use for verifying electronic circuits, solving planning problems. The graph coloring we can use to solve many different problems where we want to allocate resources in the presence of constraints. So one perhaps kind of very direct example is if we want to assign frequencies to transmitters in a wireless network such that transmitters that are close to each other aren't assigned the same frequency, because perhaps if they're too close to each other and they're assigned the same frequency, then they'll interfere with each other, so that would be bad for the network. If we want to do this, then we can think of each transmitter in the network as a vertex in the graph, and the ones that are close to each other are connected by an edge, and the color of a vertex corresponds to the frequency that transmitter is transmitting on. So then in that case, finding the minimum number of colors corresponds to the minimum number of frequencies for that wireless network. Okay, so there are many more applications of both of these problems. And as they're NP-complete, we don't expect that we'll have an efficient classical algorithm or quantum algorithm to solve them. We think that there won't be a polynomial time algorithm for either of these, but nevertheless, they can be solved somehow, sometimes surprisingly efficiently in practice using some nice classical algorithms that we have. And we would like to do better than these classical algorithms with a quantum computer. Okay, so what's the results I'm going to talk about today? So what we did is we applied two quantum algorithms, Grover's algorithm, which I guess everyone here is very familiar with, and also a quantum algorithm for accelerating an approach known as backtracking, which I'll say a bit more about in a minute. We applied these algorithms to these two tasks, to SAT and to graph coloring. And each of these algorithms achieves a kind of square root type speedup over its classical counterpart. So Grover's algorithm accelerates classical unstructured search, and this quantum approach to accelerating backtracking accelerates a class of so-called backtracking algorithms by a sort of square root. So these are not exponential speedups, but they might still be interesting. We applied these algorithms to these particular tasks. Then we tried to optimize them as far as we possibly could. So we tried to reduce the time complexity of these algorithms as much as possible. So this corresponds to the depth of the quantum circuits that we were looking at, it turns out. I'll say a bit more about the model in a minute, but basically we were trying to find the most efficient circuits that we possibly could. Although the algorithms themselves are kind of theoretically not far from optimal, there's still a lot you can do in trying to optimize the various sort of lower order terms in the algorithms, and that's something we tried to do. Then we tried to work out how long these algorithms would take to run when we applied them to particular instances of SAT and graph coloring problems. So there's an interesting question when you're trying to, let's say, compare two different classes of algorithms, quantum and classical algorithms, like what's a reasonable family of problems to compare them on? And one particular challenge you have when trying to understand how fast a quantum algorithm is going to run is that almost by definition you want to be running it on problem instances which are too hard for your classical computer to solve. So it's going to be tricky for you to run a classical algorithm on that problem instance to figure out how fast perhaps the quantum algorithm would run once you sped it up, because you just can't even run the classical algorithm on that problem instance. So one thing you can try to do is find a family of problem instances where you can figure out how long the runtime is of the algorithm on small instances, and then you can scale up the instance size, and you can hope that as the instance size scales up, the runtime also scales in some nice way, such that you can extrapolate to instances which are too large for you to actually handle on your computers today. So one nice way of getting families of instances where you can try to do this is just to pick them at random. And this somehow gets away a bit from the notion of trying to find problems that are practically interesting, because maybe these random instances don't really correspond to problems that we see in practice. But on the other hand, maybe they correspond to the really sort of challenging, unstructured parts of some more sort of structured problem instance you might see in practice. So anyway, it's a matter for debate, but in any case, choosing problem instances at random is something you can do, and these sort of random instances are expected to be hard for classical algorithms if you choose them correctly, so at least it's perhaps a reasonable sort of benchmark. So, okay, so we were trying to estimate the runtimes of these quantum algorithms, and once we've done this, we can then try to actually turn this into a real-world runtime. So for a given problem instance, given our guess for the extrapolation of the runtime, we can figure out what the quantum circuit depth is that corresponds to running the quantum algorithm on that instance size. And then we can try to turn this into a real-world runtime by plugging in some parameters for the hardware, and also for all of the other things we might have to worry about, in particular fault tolerance. And then this gives us an actual number saying that it will take a certain amount of time to execute this algorithm on this problem size. And then we can try to compare this quantum algorithm's runtime to the performance of a good classical algorithm. And a nice thing here is that in some cases there are competitions, I think Krista already mentioned this earlier, where people try to find the best possible classical algorithm for some particular task, for example, boolean satisfiability, and they come together and they bring their best algorithms and they compete to see which one's the fastest. And this means that it gives us a nice sort of target for a leading classical algorithm to compare against. And this is what we did here in the case of SAT. We took the winner of the SAT competition, I guess it's maybe 2017 now, I forget, 2017, 2018, which turned out to be this Maple LCM dist algorithm. And in the case of graph coloring, there isn't, as far as I know, a regular graph coloring competition, but there's a sort of benchmark algorithm which many people use, and it's been, seems to be competitive with many other algorithms called DSATA, and that's the one we get compared against. Okay, so and to figure out the likely performance of these classical algorithms, again, we ran them on small instances and tried to extrapolate upwards. Okay, so that's roughly the sketch of what we did. I said I would say a little bit more about backtracking on the previous slides, and I'll just describe this very briefly now. Basically, this backtracking is an approach to solving constraint satisfaction problems where we have the ability to check whether a partial assignment to some variables can be potentially extended to a full solution to the problem that we care about. Right, so I'll just illustrate this in the case of graph coloring, but it's a much more general approach that can be applied to many different kinds of constraint satisfaction problems. Okay, and in many ways it can be thought of as the most naive thing you could try for solving a graph coloring problem, other than just trying all of the different colorings one after the other in a completely unstructured way. So imagine we had this graph up here with 4 vertices and we wanted to colour it with 3 colours. Well, what would we do? Well, a very natural thing to do is just to start trying to assign colours to vertices. So we might try to assign a colour to the vertex in the bottom left here. We might try red, yellow or blue. Like if we're allowed 3 colours, we might have a choice of red, yellow or blue for this bottom left vertex. And okay, everything seems fine so far. All of those colours are okay. So let's say we choose red as our colour, then we might move on to the next vertex, maybe on the bottom right. And again, we have a choice of red, yellow or blue that we can assign this one. But we can see already that we should not assign this vertex red because there's a vertex next to it which is also red. So any colouring that contains 2 red vertices at the bottom will not be extensible to a good colouring of the whole graph because it's already failed to satisfy this constraint here. So we shouldn't carry on down that route. We should try maybe assigning it yellow. And if we do this, then if we move on to that's okay. And if we move on to the next vertex, again, we've got a choice of red, yellow or blue. But now we can see that neither red nor yellow is okay because they each violate one of the constraints. So we can only assign this one blue. And again, that's okay. And we're left with the last vertex. And now the only colour we can assign this one is yellow. And we found a good colouring of this graph. Okay, so we can see with this approach that we've only explored a small fraction of the overall tree of potential solutions, and we found a good colouring with only looking at a small number of these different possibilities. And this approach is called backtracking because when we get stuck, we backtrack up the search tree and try something else. Okay, and it turns out that this classical approach can be accelerated with a quantum algorithm. And if the size of the classical backtracking tree is t, then the quantum algorithm needs runtime that scales like square root of t up to some lower order terms. So this is a kind of Grover-style square root speedup of this class of algorithms, okay? Which is nice because these algorithms are often very effective in practice. Okay, so that's the rough sketch of what we do and what algorithms we're using. I just want to say a little bit about the cost model, like how do we work out how long our algorithms are going to take to run and how much space they're going to use. Okay, so firstly, we want to take into account all the overheads to do with fault tolerance. And to do this, we're going to use the surface code to estimate as our error correction tool and to produce these estimates. And then given this fault-tolerant quantum circuit that has all of the things in it that we need to deal with errors, we can then try to convert this into a real-world runtime, saying how long this algorithm is actually going to take to run in reality. And to do this, we have to come up with some parameters for how long gates take and things like this on our quantum computers. And I know there are experimentalists in the audience, so I'm not totally sure if I'll actually get out of this room alive, but here are some numbers that we picked. So the idea is that this first column, the realistic ones, I guess realistic maybe should be in quotes, but these are based on parameters that have already been demonstrated or are not far away perhaps from being demonstrated. And these other 2 columns are just order of magnitude improvements on this. So we don't know what's going to happen with hardware in the next few years, so let's just plug in order of magnitude improvements and let's see what we get. Though obviously you could plug in different numbers and get somewhat different results. Okay, so these are sort of very rough ballpark figures, but at least they enable us to get some numbers out at the end. Okay, so that's the rough cost model. Just say one or two more things about how we finally calculate this runtime. So we're going to assume that in our quantum circuit that it's split up into Clifford gates and T or Toffoli gates, and we're also going to assume that Clifford gates are free and that T and Toffoli gates can be implemented in the time it costs us to do one measurement. So this is justifiable by the use of some techniques for time optimal quantum computation and using the surface code, where we effectively prepare some quantum states offline, these magic states we already heard about earlier in David's talk, and inject these states into the circuit at the cost of one measurement. So these sorts of circuits involve preparing fairly large states offline and then injecting them into the circuit. But this uses a lot of qubits, but it makes the circuits quite time efficient. Then it turns out that the runtime of the quantum algorithm in the end, the real world runtime, corresponds directly to the so-called T-depth of the circuit, which is the depth of the circuit, if roughly speaking, the depth of the circuit if we only include T-gates in it, okay, roughly speaking. Okay, so I just want to, now I've talked about the model, I just want to summarize what the results are, and then I'll show you a few numbers. So there's some good news and bad news, I guess. So the good news is that we do sometimes see a speed up over classical algorithms. So in the most optimistic hardware parameter regime that we consider, we might see speedups of the order of, let's say, a factor of 10 to the 5 compared with a fast standard desktop PC for solving KSAT using Grover's algorithm. And we might see a speed up by more than 10 to the 4 for graph coloring. So this is using this backtracking algorithm approach. So these are, I guess, well, relatively large. I mean, some of you may think this is a bit underwhelming because this may not even outperform, let's say, a very fast classical supercomputer. But I guess it's worth stressing a couple of things. Like, one thing is that these are only quantum algorithms that deliver square root type speedups, so we wouldn't necessarily expect to have a quantum algorithm that runs for one day and solves one of these problems and this same problem would take a classical supercomputer, 10 years or something like that. These algorithms just, I think, don't necessarily deliver speedups that are that large. And it's also worth saying that it's not so clear that the classical algorithms for solving these problems could be parallelized perfectly, so in such a way that we could, solve these same problems just as fast by sticking it on a supercomputer. That'd be an interesting thing to understand more in the future. And it's also worth stressing at this point that these speedups here are for problem sizes that we can solve in one day using the quantum computer. Right? So we have these problem instances that we expect will take a day to solve on a quantum computer, and if you used your desktop PC, it would take you 10 to the 5 days, something like that. Okay, so that doesn't sound too bad. The bad news, well, there's, I guess, several bits of bad news. So firstly, if we consider the more realistic hardware parameter regimes corresponding to hardware that we have today, then the speedup gets smaller. So for example, it might be 10 to the 3 for KSAT, which may be less impressive. Also, perhaps more seriously, is that one thing which is kind of subtle, which also I think ought to be considered when we're doing these kind of complexity comparisons, is another cost that goes into the quantum computation, which is the cost of the classical error correction that goes into the fault-tolerant quantum computation. So when you're running your fault-tolerant quantum computation, like constantly there is a lot of error correction processing going on, which is I guess, a relatively simple classical algorithm, but nevertheless it still costs you something. And if, for example, just for the sake of argument, if we imagine that this classical error correction processing required 1 million CPUs to be running all the time during your quantum computation, well, maybe you should have just used those 1 million CPUs just to solve the problem that you had in the first place classically, rather than using them to do their error correction. So in order to get a full comparison between the quantum runtime and the classical runtime, you should probably take into account this factor, which is that you're actually using a lot of classical processing as well. And I'll say it in a little bit about how we estimated this. Okay, and the other slightly scary thing is that the number of physical qubits used for these to achieve these speedups is extremely large. So let's say at least 10 to the 12 or something like this, right? Which is very big, and almost all of these qubits are used for fault tolerance. So as I mentioned, the way that the circuits are working is doing magic state injection. So they have these factories that are producing these magic states and are injecting them into the circuit. And these factories end up needing to be very large, and there need to be a lot of them. So that's why you end up with a lot of physical qubits being used. But I guess, yeah, the good news is that almost all of these are just used for fault tolerance rather than anything kind of algorithmic. Okay, so one thing that I really found very strongly that came out of this work is that if we want to run these kind of Grover-style algorithms on a quantum computer, then I think it will be very important to have better fault tolerance techniques, because with these kind of overheads, it's going to be really a very big challenge to run these algorithms on a quantum computer. Okay, so I'm just going to summarize some numbers here for these problems that I was talking about. So this table is showing these sorts of speedups and other things we might see for solving Boolean satisfiability using Grover's algorithm in various different parameter regimes, like I mentioned. So this is all relative to a sort of fast but completely standard classical desktop machine, and this Maple LCM dist sat solver that I mentioned running on that. And this first row, like this max n, is the largest instance size we might expect to solve with a quantum computer in one day. And then these other columns are other things like the t-depth of the circuit, the number of gates in the circuit, number of Toffoli gates in the circuit. And I guess the important numbers are these bottom two, the number of qubits that we need. This is only counting the number of qubits that are used in these so-called magic state factories, but in fact that dominates the cost of the number of qubits in the circuit, number of qubits used throughout the process. And you can see that even in this most optimistic regime down here, that we might need 10 to the 12 qubits, and we get a speed up of a bit more than 10 to the 5. And the speed ups and number of qubits are a bit worse in these other two regimes. And in the case of graph coloring, things are kind of simple, only a little bit worse, the numbers actually. So we get about a speed up of 4 times 10 to the 4 in the most optimistic case. And it's interesting because I mean, this, I guess, parallels some work that was done on quantum simulation, in that somehow the quantum algorithm that we applied to this graph coloring problem is this backtracking approach, which is somehow a bit more complicated, but in principle it ought to achieve a larger asymptotic speedup than just using Grover's algorithm and applying this to SAT. But because the algorithm is more complicated, the various overheads that go into it mean that it ends up not outperforming or not achieving a larger speedup than we saw with Grover's algorithm applied to SAT. So, okay, so those are those results. And just to say a bit more about taking into account this cost of classical processing. So how did we do this? Well, we can start out by taking the runtimes reported for some fast error correction algorithms in, I guess this is the fastest algorithm, or at least where the runtimes have been reported, which is a paper by Darfoss and Nickerson in 2017. So this is an algorithm for decoding the surface code just on a standard computer. And then we can try to think about how much better we could do with more exotic types of hardware in the future. So this is a relatively simple algorithm. We might be able to do something interesting in putting it on some different kind of hardware, like maybe a GPU or an ASIC. And so we have some kind of guesswork how we can extrapolate up to these kinds of platforms. And then in the end, what we end up with is some estimates for how much classical processing it will take to implement a certain number of Toffoli gates under different types of parameter regimes. And we considered this for different types of hardware, like CPUs, GPUs, and ASICs. And in the end, if we want to implement, let's say, 10 to the 20 Toffoli gates, which is about the number that we need for these algorithms, then using these current algorithmic techniques and with some guesses for how the hardware will scale in the future, we might need like 3 times 10 to the 8 processor days to do all of the error correction processing throughout the computation. So this is a bit scary because this wipes out the speed up that we saw previously. So this really suggests to me that we might need either better decoding algorithms or some clever way of understanding how to implement this in hardware. Or maybe someone can just improve the estimates here, because I'm sure they're very, very rough. Yes, but I mean, one thing I should say though, which is I guess a nice thing in some sense about these scary numbers coming from top fault tolerance, is that at least the complexity of the algorithm has been somehow decoupled into an algorithmic part and then a sort of fault tolerance part. So improving the fault tolerance part would, is a sort of separate endeavor to improving the algorithmic part. So so it can be done in some sense separately, and any improvements in fault tolerance could feed into improvements to these complexities. Okay, so the very final thing I want to say briefly is something which I guess is much closer related to NISQ, although I don't have very much to say yet, which is just to mention a quantum software startup, Facecraft, which was founded by Toby Qubit, who's here, and John Morton and myself. And this is a quantum software startup where the goal of the company is basically to do exciting things with near-term quantum hardware. And we're particularly interested in quantum simulations at the moment, and focusing especially on many-body physics, perhaps. And I'm pleased to announce that we finalised our first funding round fairly recently. So we've been able to start building up a team, which is shown here. And we even have an extremely informative website, which I urge you to check out. But I guess one reason for mentioning this is just to say that although the numbers that I mentioned earlier in the talk clearly are much more of a long-term thing, I think that there are many exciting things that can be done with near-term hardware that we should look for in the regime between now and when we get up to these very large numbers of qubits that we'll need for running these Grover-style algorithms later on. Okay, so just to conclude my talk, I'd just like to summarize that I think the message is good and bad news, that we might be able to achieve a fairly significant quantum speedup for some very common problems that are of some practical relevance, which I think, at least to me, was not clear when we started this work. It wasn't clear to me that we would see any speedup at all for solving these NP-complete problems with a quantum computer. But on the other hand, there are a lot of challenges we need to solve before we get there. And if we had better fault tolerance techniques, this would really make a big difference to this. So this is everything I wanted to say, so thanks very much.
Thank you, Ashley. Are there any questions?
You were mainly considering T cost, and my question is, did you take into account geometrically local gates?
Yep. No. So there are two things we did not take into account in this analysis, which I would say this is like the first stage of the analysis you would want to do. There are much more precise types of analysis that people have done for other problems. So the two things we didn't take into account are geometric locality and also sort of space-time cost, in the sense of you can have some difficulties if you want to pack too many gates into too small a volume, and then you have to worry about kind of spreading things out in such a way that you avoid this. So we didn't take this into account. One thing I would say though is that for these kinds of algorithms, almost all of the cost is this kind of outer loop that has many iterations, like a sort of Grover-style algorithm which has many iterations, and the cost of kind of routing and geometrically local considerations is somehow quite a low order one. So I don't think it would make a gigantic difference, but it would make a difference, I think.
Okay, thank you.
Any other questions?
So both of the problems that you considered are NP complete, so they can both be mapped onto each other, and yet these speedups that you find are very different. So of course that somehow exemplifies again that mapping problems onto each other can actually have a huge impact. So does this also, or is this not also a bit concerning when one tries to gauge the the relevance of such, I would say, synthetic benchmarks of random pools, because like if I have a real problem which is also NP complete, and then I don't know, I can map it to graph coloring, or I can map it to KSAT, and then I use your algorithms for like either of those. I would get vastly different results. So I don't know if you have any thoughts on that.
Yeah, I mean, I think this is a good point. I mean, I think that there are several concerns with using these kinds of benchmarks for practical quotes things. And yeah, I mean, I think, one thing I would say is that somehow with these benchmarks, one thing we were looking for is the hardest instances for classical algorithms, right? So you look for things where the classical algorithm can't find any structure to exploit. And I guess that the hope is that that corresponds to the problems which are super hard for those classical algorithms in practice. So if you have a SAT solver that has all sorts of nice routines built into it to deal with particular kinds of structure, then this might really struggle if you have to have a random instance. And so it may be that random instances are a good model for the ones where it does struggle. But basically, we don't know. And I think, in the long run, we will have to run these algorithms on real-world problems that that are small enough that we can actually run them and see how they perform. But because I think, I think choosing benchmarks is a very big challenge and a very interesting challenge.
This is probably just a question that shows my ignorance, but I was wondering, you talked about losing the practical advantage when you account for the fault tolerance overhead. Do you lose these Grover advantage? Can you lose the Grover advantage asymptotically because of the fault tolerance overhead?
No, because in fact, if what you care about is runtime, then the techniques we used give you no disadvantage in some sense, because we're using these kind of time optimal things where in fact each gate in your circuit just corresponds to one measurement, or pretty much, that you're doing.
But you have to do classical computation.
Yes, you have to do classical right. So in the long run, the asymptotics I think will win out. But I think as soon as you have this restriction to have sort of realistically small sizes, then I think you can run into problems.
Any other questions? If not, let's thank Ashley again.